One very common method we have for measuring the level in a tank is a thing called the bubbler. The bubbler works on the principle that we have a very small amount of air bubbling out of the end of an open pipe. Just enough to make small bubbles rise up, just quite slowly, in this sort of bubble, 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 about 1 a second. Not massive amounts of bubbling. If you have too much pressure in this bit of pipe, then it comes out like a siphon, and that's no bloody good at all. So you just need very slow bubbles coming out of this bit of pipe. We use a special machine called a pneumostat. Now what a pneumostat does is you fill the pneumostat up with whatever you happen to have in the tank. And so you fill the pneumostat up, and as the air goes into the pneumostat, it bubbles. So we see bubbles, oops, wrong colour bubble. We see bubbles in the pneumostat as the air goes through. And because the pneumostat is filled with the same stuff as happens to be in the tank, the rate at which it bubbles through the pneumostat is the same as the rate at which it bubbles through the tank. We do this because quite often we can't see the tank. So if we adjust the airflow through the pneumostat and we adjust the air pressure through the pneumostat until we just get 1 bubble a second, that's good. Now the idea of this is we measure the pressure in that bit of pipe. If anything blocks up the end of the pipe, which is here, if anything blocks up the end of the pipe, it causes back pressure, so the pressure gauge reads higher. The sort of thing I'm talking about blocking up the end of the pipe is the fact that the level in the tank is rising. As the level in the tank rises, it back pressures the end of the pipe. And as the end of the pipe gets blocked up by the level rising, the pressure here increases. So it's a very simple way of measuring the level in the tank. As the tank fills up, this gauge reads a higher pressure. The bubbler is a very, very, very common level measuring system. It's probably the most common level measuring system. Places we use bubblers are in bores. If you have a bore and you need to know what the level in the bore is, that bore might be 300, 400, 500 meters deep. All you need to measure the level in that bore is to stuff a pipe down it. You just shove a pipe down it, blow bubbles through the pipe, and measure the pressure in the pipe. And that will tell you the level in the bore. Other places that use bubblers are nuclear reactors. See, the problem with a nuclear reactor is, if you've got a nuclear reactor, you have to maintain it in water. So if that's a nuclear reactor, oops, let's get a red. If this is a nuclear reactor here, we have to keep the fuel cells underwater. Now, we have to always maintain the fuel cells underwater, otherwise it explodes, and that's, a bad thing. So we need to know the level in the nuclear reactor. Now, the big problem with nuclear reactors is all that radiation will kill any electronics we have. The nice thing about a bubbler is that any electronics we happen to have, which might be on the pressure sensor, this pressure sensor here, that can be hundreds and hundreds of meters away from the nuclear reactor. So using this on nuclear reactors, all that we need to stick into the reactor vessel itself is a piece of nylon pipe, which is completely inert and completely safe. We don't have to worry about it. So that's the bubbler, very common method of measuring level. Another thing you can do is have 2 bubble pipes. Let's just grab another bubble pipe. If I have 2 bubble pipes, and they are there, pen, there. That's my other bubble pipe. and I've got bubbles rising out of that. If these two bubble pipes are in the same piece of tank, and they're separated by the ends of them, if the ends of the bubble pipe are exactly, say, 1 meter apart, then one of them will measure one pressure, and the other one will measure a second pressure. Just finish this off. The difference between those two pressures will be due to the fact that there's 1 meter difference in the two heights. Now, if I happen to know that there's exactly 1 meter difference between the two heights, I can say that because P equals rho GH, then the difference between one of the pressures, I'll call this one number 1 and this one number 2, I could say pressure 1 equals rho GH, pressure 2 equals rho GH. Now, this is going to be H1. This is going to be H2. Now, H1 is 1 more than H2. So what I can do is I can say this is going to be rho GH2 minus 1. So there's a difference between those two pressures, and what it works out as is the difference between those two pressures is due to 1 meter in height difference, which I happen to know. So really, by knowing that there's exactly 1 meter of height difference between them, I can actually work out what the density is, because the density in the tank is the same for both pipes. The only thing that really changes between these two pipes is 1 meter of height. So what I can say is P1 minus P2 is caused by 1 meter of height equals rho G times 1. It's a 1 there. And because G is a constant, the difference in those two pressures gives me the density. So 2 bubblers in one tank is measuring density. Okay, that's enough about bubblers. We have a saying in instrumentation, and that saying is, when all else fails, nuke it. If you're having a particularly hard time measuring the level in a tank, then nuke it. Stick a radioactive source on one side of that tank and measure the radiation on the other side. And let me just draw a quick sketch of how that would look. So what you do is, I've probably got a better drawing in here somewhere. You have a tank with a level in it. For some reason, you're having difficulty measuring that level. What you do is, you stick a big fat, where are you? You stick a big fat radioactive source on one side of the thing, and that shines radiation through the tank, and then you put a big long tubey thing up one side which measures that radiation with a radiation sensor at the top or at the bottom. And then the higher the level in the tank, if we assume that the stuff that's in the tank is quite dense, the more there is in that tank, the more radiation gets absorbed, so the less ends up coming out the other end. So by measuring the amount of radiation that gets through, we know how much is in the tank. Now, hopefully you're saying to yourself, I don't like the sound of radiation. And you'd be quite right to not like the sound of radiation. Radiation is not nice stuff. It's dangerous. It kills. It damages you. It causes radiation sickness and poisoning. And it's not nice stuff. The radiation source itself is kept in a great big box, lead-lined, with all sorts of locking mechanisms so that it can be locked off. It comes out through a very small pipe. But this is not nice stuff. It has to be treated with respect. Different types of radiation penetrate different distances. Alpha radiation, which is basically nucleuses, that can get, because it's big and fat, it can get stopped by relatively thin things like a sheet of aluminium. Beta radiation, which is energized electrons, that can get through a couple of sheets of steel. Gamma radiation, well, that can get through quite a bit of lead. So different types of radiation can go different distances. Most radioactive sources, or even if it's a beta source or an alpha source, usually gives out a bit of the other. So you normally get all sorts of radiation coming out of any radioactive source. We talk about a half-value layer. When we're talking about radiation, we have to start talking about the shielding we're going to put around that radiation. And we talk about this thing which is the half-value layer, which is how much of something we need to decrease the radiation by half. So if you have a radiation source which is cesium-137, you need about 14 millimeters of steel to reduce that radiation to half its value. Or 90 millimeters of water or 40 millimeters of concrete. If your radiation source is cobalt-60, which is a much more powerful source, you need about 20 millimeters of steel to reduce that radiation to half its value, or 12 millimeters of lead. That's quite a lot. That reduces the radiation to half its value. It doesn't reduce the radiation to necessarily a safe amount. One thing that makes radioactive sources particularly unpleasant is that the radiation never really goes away. If you take, for instance, cobalt, if you get a radioactive source of cobalt-60, and say you've got 100 grams of cobalt-60, cobalt-60 has got a half-life of 5.3 years. What that means is, if you start with 100 grams of radioactive cobalt, in 5.3 years, you have, if you start with 100 grams of it, in 5.3 years, you have 50 grams of radioactive cobalt and 50 grams of non-radioactive cobalt. Now you only have half as much radioactive cobalt. And if you only have half as much radioactive cobalt, it's only producing half as much radiation. So it's only half as dangerous. Unfortunately, it's also only half as useful, because it's like a light bulb that's dimmed. So generally speaking, 5.3 years down the line, we need to replace it. So we take it out and we put it in a cupboard, because we can't throw it away, and it sits in that cupboard. 5.3 years later, we have half as much again. Now what that means is we had 50 grams of radioactive cobalt. 5.3 years later, that's decreased by another 25 grams. So now we have 25 grams of radioactive cobalt and 75 grams of non-radioactive cobalt. 5.3 years later, we have half as much again. Now we've got 12.5 grams of radioactive cobalt. So what we're 15 odd years down the line, and we've still got radioactive substance on site. With cesium, the half-life is 30 years. Because we've got this radioactive substance on site, because we're storing it, we have to have all sorts of licensing in place. We have to have radiation officers on site. It has to be inspected. It has to be checked. It's a huge nightmare of paperwork. But if all else fails, then we have to nuke it. As we go through the course, we'll talk about more times. You'll be surprised how many times, how many substances that we end up nuking in order to measure them. We talk about radiation exposure. We talk about in terms of sieverts. Sieverts is a measure of biological effect. Basically, it goes along the lines of 1 sievert will make you ill, 3 sieverts will probably kill you, and 6 definitely will. The sort of radiation you're typically going to pick up if you fly in an aeroplane is about 52 microsieverts. The sort of radiation you might pick up just walking around the ground is about 0.3 of a microsievert. If you take a long plane flight, you'll pick up the same amount of radiation as if you had a chest X-ray. So the radiation sources we're using in industry are relatively low energy sources. That's not to say we shouldn't treat them with great respect, and if possible, walk around them rather than walk past them. This is how it works. We stick the radioactive source on one side of a tank, and we measure the amount of radiation coming out of the other side of the tank. The higher the level in the tank, the more radiation gets through. It's really as simple as that. It will ignore virtually everything. It won't care about foam, it won't care about dust. It doesn't really care what's in the tank. It will just give you a measure of the level. Now, the thing at the other end, which is measuring the level, which is receiving the radiation, let me just point to it, this thing here, that's actually a specially made piece of glass or a special tube filled with a special gas. It's very accurately made, it's very delicate, very easily broken. At the bottom of that is a Geiger-Müller tube, which is basically a tube from well, it's a radiation detector, the things that people carry around and go dick, 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 that sort of thing. The tube above it, the glass rod above it, is called a scintillator. And what it does is it's a specially made glass that will absorb radiation and channel it like fiber optic to the bottom. When it gets to the bottom, it produces a tiny flash of light, which we put through a photomultiplier. A photomultiplier is those things they use on night vision scopes. It multiplies any available light and makes it brighter. So the tiny flash of light from the radioactive particle goes through the photomultiplier and produces quite a bright flash. We then measure that flash. So that's the radiation method of measuring a tank, and if all else fails, we use radiation. Okay.